Hello everyone, how are you? In this video we're going to solve some example regarding Green's theorem. If you remember, we wrote the line integrals in terms of differentials by changing the r prime of t to dx dt and dy dt and multiply by dt. Then when the dt was cancelled out, it become dx dy, and it become the x component times dx plus the y component times dy. And then from then we tie the differential form to Green's theorem. And the condition for Green's theorem is if you have a curve and the curve is counterclockwise and it is a simple region. Simple region means there is no other region inside here, or the curve do not overlap. We can use Green's theorem. And Green's theorem tie the line integrals to the area of a region by taking the partial derivative of the y component of the vector field respect to x minus the partial derivative of the x component respect to y dA. Okay, in here this is your x component. I'm going to call my x component m, and that is 2 arctangent of y over x. I do need the partial derivative of this one respect to y. I have a constant multiple. The derivative of arctangent is u prime divided by 1 plus u squared. This is your u, and derivative of this one respect to y is the coefficient of y, which is 1 over x divided by 1 plus u squared. And if I simplify that, that become 2 times, on the bottom I get a common denominator, which is x squared plus y squared, 1 over x. Then I multiply by the reciprocal, it becomes 2x squared over x divided by when I multiply by reciprocal, that becomes 1 over x, and x squared goes on the top, and x times x squared plus y squared goes on the bottom. And this is 2x over x squared plus y squared. Partial derivative of n respect to x is, this one is your n, and the derivative of natural log is 1 over u du. Respect to x is 1 over u times du, which is 2x. Let's talk about the path. You know, if I isolate sine and cosine, sine squared plus cosine squared is 1. Therefore, that becomes x minus 4 over 2 equal to cosine theta, and y minus 4 equal to sine theta, and sine squared plus cosine squared is 1. Therefore, quantity x minus 4 squared over 4 minus y minus 4 squared over 1 is 1. And this is an ellipse with the center of 4 and 4. And then your a squared is 4, 2 to the right and left, 1 unit up. This is an ellipse. This is a counterclockwise. It is a simple region. Then you can apply Green's theorem. What is the Green's theorem? Is the area of a region, partial derivative of n, which is 2x over quantity x squared plus y squared, minus partial derivative of m, 2x over x squared plus y squared dA. Oh, they are same. That's 0. Means that vector field is conservative, And since this is a conservative, you can find the potential function. And since it's conservative, the curl is 0. Therefore, that answer is 0. That was an easy problem. That was good. I'm going to work another problem, and that is another vector field, which that's your x component and that's your y component. And your curve is bounded by these graphs, by the graph of these equations. Therefore, if this one is x-axis and a y-axis, this is the square root function y equal to square root of x. That's the line of y equal to x, and they intersect at 1 and 1, 0, 0. And I must go counterclockwise in order to apply Green's theorem, and that's very good. My region, I'm gonna make my x fixed, my y varies. The bottom one is x, the top one is the square root of x, and I'm gonna write this one dy dx. But I'm gonna apply Green's theorem, and I'm gonna say this is my m, and partial derivative of m. Remember, m is always, I call the x component, you know, mn. M is the x, n is the y. Partial derivative of n, m respect to y, is negative sine of y. That's not bad. But partial derivative of n respect to x is y minus, doing it respect to x, you have a sine of y. Then I do need partial derivative of n respect to x minus partial derivative of m respect to y. Whatever that one is, I'm gonna set it as an integrand, and I'm gonna evaluate. Respect to n is y minus sine of y minus, that one is a negative sine of y. Therefore, you have y minus sine of y plus sine of y. Your answer is y. And what is the integral of y respect to y? Is y squared over 2 from x to square root of x. When you square the square root of x, you get x over 2 minus x squared over 2. Now we're going to integrate x over 2 minus x squared over 2 from 0 to 1 respect to x. I'm going to get a common denominator and move the 1/2 out. The integral of x is x squared over 2. The integral of x squared is x cubed over 3 from 0 to 1. And that's 1/2 times 1/2 minus a 1/3. This is 3 minus a 2 is 1 over 6. And the answer is 1 over 12. Okay, that was the examples regarding Green's theorem. Now, if you remember, we took the curl of the vector f and dot it with a unit vector, and that became exactly the Green's theorem. Then instead of the Green's theorem, we put the curl of f dotted with a k over a region dA. That was the Stokes theorem. And Stokes said, if you have a surface, and surface is oriented. Oriented means you do have a normal vector that the circle, the curl can rotate around it, and the projection of the surface is a curve, and the curve is exactly what Green's theorem said, counterclockwise. Then you can find the circulation of, if it's a fluid or whatever it is in here, in circulation inside the surface. Okay, we're gonna work one problem regarding Stoke's theorem. We will discuss Stoke's theorem in a future application, in the future videos, but it's not gonna be much different. Stoke's theorem said, yes, just like Green's theorem, which tie the line integrals to the area of a region. Stoke's theorem was born from a Green's theorem. Therefore, if Green's theorem ties to a line integral, Stoke's theorem is also tied to a line integral. Then I want to evaluate that line integral, and that line integral provides us with a circulation. And remember, that was the circulation. Same formula for the work along a curve. Therefore, your curve is oriented counterclockwise as viewed from the top by using the surface. Therefore, if this is your x and y z, if x and y is 0, your z is 9. Therefore, you do have a semi-sphere right here, a semi-sphere, and that is an oriented surface, and it does have a normal vector. And somebody say, what is your normal vector? Your normal vector is the gradient of the function, because whatever your level curve is, your normal vector, your gradient at any given point is going to be normal to the level curve. Therefore, whenever you do integration, you summing up. You summing up what? You summing up all the curve dotted with the normal vector. Here, you take whatever that circulation is. There is a circulation here, there is a circulation, and all the circulation, remember, you have to think of patch. See, you have a patch and you have a normal vector. There is a circulation here. You take another patch, you have a normal vector here, which is your gradient. And then take the circulation of that one, circulation of that one, circulation of that one. You have to do it one patch at a time. Then find the sum of the circulation over all the patches, and that become over a surface ds. Remember, it's not going to be like Green's theorem to become area of a region, because we do a surface. And remember, surface is two-dimension, region is also two-dimension. Instead of a normal vector, I use the gradient of the surface over its magnitude, and that becomes exactly a unit vector. And arc length is always the square root of partial derivative of x squared plus partial derivative of y squared plus 1, and dy dx, let me call this one a dA. And if you sum it up, you get the s. But somebody said, what is this? That is exactly partial, is the magnitude of the gradient of the surface. Therefore, this is a partial with respect to x, this is a partial with respect to y, and that's the partial with respect to z. And if you take the magnitude of the gradient, you get that one. Therefore, that becomes the magnitude of the gradient, but that becomes dA, because the surface becomes the magnitude of the gradient of dA, and that's gone, and that's become a region. You take the curl of f, dotted with the gradient dA, and that you take one patch at a time and find the total circulation. Then first thing, I need my curl. Okay, then what is my curl? My curl is the operator cross it with the vector field is ijk, and then you have partial respect to x, partial respect to y, partial respect to z of 4xz y 4xy. Therefore, your I component is the partial derivative of the z component with respect to y, which is 4x, minus partial derivative of the y component with respect to z, which is 0, minus a j, partial derivative of z component with respect to x, which is a 4y, and partial derivative of the x component with respect to a z, which is a 4x. The z component, the k component is partial derivative of the y component with respect to x and partial derivative of the x component with respect to y. Therefore, you have 4xi minus 4y minus a 4xj plus 0k, that's your curl of the vector f. Okay, I got the curl, I need my gradient. Gradient, because you have to be in 3D, you have to write your z. You have to write a function of 3 variables. And in here, sometimes they ask you if it depends to your it depends which one you bring to one side. But to me, it doesn't matter if you bring all this x squared, y squared, and 9 to this side, or take the z to other side, because eventually you have to square those numbers for the arc length. For the arc length, doesn't make any difference. But for the gradient, because you're gonna dot it with this one, you want to make sure you always do circulation clockwise around the positive side. Therefore, I'm going to use this one because this is going to be above xy, because that's a z positive. Therefore, I'm going to write a function g of x, y, z, and keep the z right here, but I bring the 9 and x and a y to other side, and I said, what is the gradient of the g? Respect to x is 2x, respect to y, 2y, respect to z is 1. And if this z become a negative 1, you be okay, but your answer gonna have a maybe different sign. It depends what the z component of the curl is, and so on. Okay, then I'm gonna go right here and say, okay, I got the curl, I got the gradient. What is the curl of f dotted with the gradient of g? I have 4x plus 4x minus a 4y. I just distribute the negative, 0, and I dotted with 2x, 2y, and a 1. Therefore, in here you have 8x squared plus 8xy plus minus 8y squared plus 0. Let me make sure I did it right. 8x squared, 8xy minus 8y squared. I got it. Therefore, I have 8x squared plus 8xy minus 8y squared dAr. Somebody said, what is your A? Look at your surface. Is the same dA as the Green's theorem. Is that region. That curve. That curve is a projection from the top. Projection of the surface on the xy. Means z is 0. And if z becomes 0, you have x squared plus y squared equal to 9. Then your region is a circle with a radius of a 3. I go from -3 to 3. Your y goes from a negative square root of 9 minus x squared to 9 plus x squared. And I'm going to have 8x squared plus 8xy minus 8y squared. My y changes, my x is fixed. I don't think this problem is going to be very hard to do, because integration respect to y is 8x squared y plus 8x y squared over 2 minus 8y cubed over 3, and this goes from negative square root of 9 minus x squared, and this one is 9 minus x squared, and here I put a plus, that should be a negative, and you can plug it in and that become 8x squared 9 minus x squared plus 8x, 8 over 2 is a 4, y squared become 9 minus x squared, and that's the 8/3. When I cube that one, that become a negative, negative times negative become a positive. You have 3 of these. You have 9 minus x squared times the square root of 9 minus x squared. Then you're going to evaluate this one from negative to 3 to 3 and dx. You know, this is going to take a few minutes of time. I'm going to leave this one up to you. It's not very hard to do. Here you have to do u substitution, 9 minus x squared equal to u, and then solve x squared in terms of a u. But this one you can do the power rules, and in here you can break it to 2, and it's going to be, some of it is going to be trig substitution and some of it is going to be similar to that one. And this is nothing except Stoke's theorem, and that's an example of Stokes. But what Gauss did, Gauss was another mathematician, which we did in the last video, that he took the vector field and said Gauss projected over the vector field over the unit tangent. Let me make this one a little bit better looking. He said the Stokes projected over the unit tangent vector, but Gauss did it over the normal vector. And they said if this one was a unit tangent vector was x prime and y prime, the normal vector would become, let me call this one a little n. Unit vector, you change the x and y, that become y prime, and that become x prime, but I changed the sign of 1. But this is called flux out. Therefore, that's my n, and that's my n becomes, you switch the sign, is negative y prime, comma, x prime. And then if I write this one as a vector field of m and n, and dot it with dy dt with a negative, comma, dx dt, these are gone, and that's become the differential form become negative m dy plus n dx. And Mr. Gauss said, if I go to Green's theorem and I said I have a dA here, this is partial derivative of n respect to x. But what is this? Remember, this is exactly the same as m dx plus n dy. Right now on the flux, your negative n become an n, and this become your what? That become your m. Therefore, whenever I apply it into a Green's theorem, you have minus partial derivative of m respect to y. Right now this is your n, and that's supposed to come in place of this one. I'm sorry, it has to come in place of that one, because this is your n, and that's become a negative m, and that m, which is a y, that should become an n. And I did exactly same thing in the last video. This one I am okay, negative m dy, and in here I'm switched the sign of x. Therefore, tell me what this one is. The x go that way, really, because the x going that way, that should be a positive and that's become a negative, and when you come in here, that should become a positive and that should become a negative. Nope, that's the positive and that's the negative. In here I should have both positive, because if I factor a negative, this is going to come in, but I want it to go out, become partial derivative of m respect to x plus partial of n respect to y dA, and that's the double region. Let me see what I got a negative right here, because I want my negative m partial derivative of n respect to y minus partial derivative of n respect, and this is respect to x, respect to y dA. I want this to become a negative n, and negative times negative make it a positive. Okay, let me see what I have. I need a negative n, therefore this one I'm gonna make it a negative, make this one a positive. This is positive, this is a negative, this is a positive, this is a negative. Right now I have m dy minus n dx. Then I'm gonna have m, my n is m now. This is your m. And your m is negative n. And negative times negative make it a positive, and that becomes the divergence. And remember, the sign is just in and out, but it had to be positive for out and negative for in, and that becomes plus partial of n respect to y. And we proved this one in the last video, and that's exactly what we're gonna do. But remember, this one was in a plane. What happened when you have divergence and you have a surface? Oh, this one, we proved it. This is nothing except the divergence, and the divergence was operator dotted with a vector field, and the operator was partial of x, partial respect to y, and partial respect to z. And this one was your vector field m, n, and a p, and that was exactly your divergence. And this is what you see. That is your divergence right here, and that's what we need to do. Okay, let's go to the problem and say, what is my vector field? My vector field is this one. I'm going to find this divergence, partial derivative of x. I'm going to make the divergence of the vector field. What is the partial derivative with respect to x? Is y squared, and this one is a constant, is 0, plus respect to y is x squared, and this one is a constant, is 0, and respect to z is e to the power of z. That's my divergence. And your divergence on this surface is going to be the volume, and if it was a region, you put a dr, and this is the divergence of the f. Okay, I got my divergence, but I need the volume of that one. Well, in here, when z becomes 0 is a point, z become 1 is a circle, and when z become an 8, that become x squared plus y squared equal to 256. Therefore, this is nothing except a plane at x equal to 8, and then you have a cone, which that cone right here, since your z is 8, in here you have 16 equal to a square root of x squared plus y squared, and x squared plus y squared equal to 256. Therefore, the projection of it is going to be that circle. Okay, I can go right here and maybe change it to a cylindrical coordinate. And I said, my angle is from 0 to 2 pi. My r is from 0 to 16. My z is from here, that's the low z, and that's the high z. Your z is 8. But in here 1/2 x squared plus y squared, I'm going to put r squared. And I need my divergence. My divergence is x squared plus y squared, which is r squared plus e to the power of z. But I do have a dz, I have a r, dr, d theta. And I am done for the divergence. Let's do this one respect to z is r squared z plus the integral of e to the power of z is e to the power of z. And I'm going to do this one from 1/2 r to 8. That becomes 64. Let me see, what did I do? That's right. In here, why 64? That's your z. 8 r squared plus e to the power of 8 minus 1/2 r cubed plus e to the power of 1/2 r. Right now I have another r in here. Therefore I have 8 r cubed plus r e to the power of 8 minus 1/2 r to the power of 4 plus r e to the power of 1/2 r dr, and your r is from 0 to 16. Okay, this one is 8 r to the power of 4 over 4 plus e to the power of 8 is a constant, r squared over 2 e to the power of 8 plus minus 1/2 r to the power of 5 over 5, but this is r e to the power of 1/2 r. I have to do integration by part. My u is r, my du is dr, my dv is e to the power of 1/2 r dr. I do need a 1/2, therefore my v is 2e to the power of 1/2 r. Then for that one I have plus 2r e to the power of 1/2 r minus 2 e to the power of 1/2 r dr. And this is integrable. I need a 1/2 here. 1/2 I multiply by another 2, that's become a -4 e to the power of 1/2 r, all from 0 to 16. Okay, then I have 8 over 4 is 2, 16 to the power of 4 plus 6, that's this 16, 16 times 16, but 16 over 2 is 8. That's 8 times 16 e to the power of 8 minus 1/2 1 over 10, and this one your r is 16 to the power of 5 plus 2 times 16 is 32, e to the power of half of 16 is 8 minus 4, e to the power of half of 16 is 8. All of these respect to d theta from 0 to 2 pi. Remember, all of these are constant. All of them are constant. Therefore, this becomes theta. Therefore, what I need, I have this and this. You can combine them. You can combine all of this one. It's going to be some number times 2 pi. And that become your divergence. Therefore, remember, Green's theorem, Mr. Green contribute a lot into physics and science, and also helping us to solve the line integral. From there we got Gauss theorem, which is the divergence theorem, and also we got the Stoke, which is the circulation. Remember the circulation. Circulation, when you have a space, and you have a space, you have to do dispatch, 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 and every one of these patch has, that patch is so tiny, has a normal vector, normal vector, normal vector. Therefore, you take all those circulation and sum it up over the surface. Thank you, and I hope you enjoyed the video. See you on the next video.